Benzene.
Benzene is an organic chemical compound with the molecular formula C6H6. Its molecule is composed of 6 carbon atoms joined in a ring, with 1 hydrogen atom attached to each carbon atom. Because its molecules contain only carbon and hydrogen atoms, benzene is classed as a hydrocarbon. Benzene is a natural constituent of crude oil, and is one of the most elementary petrochemicals. Benzene is an aromatic hydrocarbon in the second annuline, a cyclic hydrocarbon with a continuous pi bond. It is sometimes abbreviated PHH. Benzene is a colorless and highly flammable liquid with a sweet smell. It is mainly used as a precursor to heavy chemicals, such as ethylbenzene and cumin, which are produced on a billion kilogram scale. Because it has a high octane number, it is an important component of gasoline, comprising a few percent of its mass. Most non-industrial applications have been limited by benzene's carcinogenicity.
History. Discovery.
The word benzene derives historically from gum benzoin, sometimes called benjamin, that is, benzoin resin, an aromatic resin known to European pharmacists and perfumers since the 15th century as a product of Southeast Asia. An acidic material was derived from benzoin by sublimation, and named flowers of benzoin, or benzoic acid. The hydrocarbon derived from benzoic acid thus acquired the name benzene, benzol, or benzene. Michael Faraday first isolated and identified benzene in 1825 from the oily residue derived from the production of illuminating gas, giving it the name bicarborate of hydrogen. In 1833, Eilert Mitscherlich produced it via the distillation of benzoic acid, from gum benzoin, and lime. He gave the compound the name benzene. In 1836, the French chemist Auguste Laurent named the substance phene. This is the root of the word phenol, which is hydroxylated benzene, and phenol, which is the radical formed by abstraction of a hydrogen atom, free radical H from benzene. In 1845, Charles Mansfield, working under August Wilhelm von Hofmann, isolated benzene from coal tar. 4 years later, Mansfield began the first industrial-scale production of benzene, based on the coal tar method. Gradually the sense developed among chemists that substances related to benzene represent a diverse chemical family. In 1855 August Wilhelm Hofmann used the word aromatic to designate this family relationship, after a characteristic property of many of its members. In 1997, benzene was detected in deep space.
Ring formula.
The empirical formula for benzene was long known, but its highly polar and saturated structure, with just 1 hydrogen atom for each carbon atom, was challenging to determine. Archibald Scott Coupeau in 1858 and Joseph Loschmidt in 1861 suggested possible structures that contained multiple double bonds or multiple rings, but too little evidence was then available to help chemists decide on any particular structure. In 1865, the German chemist Friedrich August Kekuele published a paper in French, for he was then teaching in Francophone Belgium, suggesting that the structure contained a 6-membered ring of carbon atoms with alternating single and double bonds. The next year he published a much longer paper in German on the same subject. Kekuele used evidence that had accumulated in the intervening years, namely, that there always appeared to be only one isomer of any monoderivative of benzene, and that there always appeared to be exactly 3 isomers of every derivative, now understood to correspond to the ortho, meta, and para patterns of arene substitution, to argue in support of his proposed structure. Kekuele's symmetrical ring could explain these curious facts, as well as benzene's 1:1 carbon-hydrogen ratio. The new understanding of benzene, and hence of all aromatic compounds, proved to be so important for both pure and applied chemistry that in 1890 the German Chemical Society organized an elaborate appreciation in Kekuele's honor, celebrating the 25th anniversary of his first benzene paper. Here Kekuele spoke of the creation of the theory. He said that he had discovered the ring shape of the benzene molecule after having a reverie or daydream of a snake seizing its own tail. This is a common symbol in many ancient cultures known as the Ouroboros or endless knot. This vision, he said, came to him after years of studying the nature of carbon-carbon bonds. This was 7 years after he had solved the problem of how carbon atoms could bond to up to 4 other atoms at the same time. It is curious that a similar, humorous depiction of benzene had appeared in 1886 in the Bericht der Durstigen Chemischen Gesellschaft, Journal of the Thirsty Chemical Society, a parody of the Bericht der Deutschen Chemischen Gesellschaft, only the parody had monkeys seizing each other in a circle, rather than snakes as in Kekule's anecdote. Some historians have suggested that the parody was a lampoon of the snake anecdote, possibly already well known through oral transmission even if it had not yet appeared in print. Some others have speculated that Kekule's story in 1890 was a re-parody of the monkey spoof, and was a mere invention rather than a recollection of an event in his life. Kekule's 1890 speech in which these anecdotes appeared has been translated into English. If the anecdote is the memory of a real event, circumstances mentioned in the story suggest that it must have happened early in 1862. The cyclic nature of benzene was finally confirmed by the crystallographer Kathleen Lonsdale in 1929.
Early applications.
In the 19th and early 20th centuries, benzene was used as an aftershave lotion because of its pleasant smell. Prior to the 1920s, benzene was frequently used as an industrial solvent, especially for degreasing metal. As its toxicity became obvious, benzene was supplanted by other solvents, especially toluene, methylbenzene, which has similar physical properties but is not as carcinogenic. In 1903, Ludwig Roselius popularized the use of benzene to decaffeinate coffee. This discovery led to the production of Sanka. This process was later discontinued. Benzene was historically used as a significant component in many consumer products such as liquid wrench, several paint strippers, rubber cements, spot removers and other hydrocarbon-containing products. Some ceased manufacture of their benzene-containing formulations in about 1950, while others continued to use benzene as a component or significant contaminant until the late 1970s when leukemia deaths were found associated with Goodyear's Pleo film production operations in Ohio. Until the late 1970s, many hardware stores, paint stores, and other retail outlets sold benzene in small cans, such as quart size, for general-purpose use. Many students were exposed to benzene in school and university courses while performing laboratory experiments with little or no ventilation in many cases. This very dangerous practice has been almost totally eliminated.
Structure.
Benzene represents a special problem in that, to account for the bond lengths quantitatively, there must either be electron delocalization, molecular orbital theory, or a spin coupling of the p orbitals, valence bond theory. X-ray diffraction shows that all 6 carbon-carbon bonds in benzene are of the same length, at 140 picometers, pm. The CC bond lengths are greater than a double bond, 135 pm, but shorter than a single bond, 147 pm. This intermediate distance is consistent with electron delocalization. The electrons for CC bonding are distributed equally between each of the 6 carbon atoms. Benzene has 8 hydrogen atoms fewer than the corresponding parent arcan, hexene. The molecule is planar. BMO description involves the formation of 3 delocalized p orbitals spanning all 6 carbon atoms, while in VB theory the aromatic properties of benzene originate from spin coupling of all 6 p orbitals. It is likely that this stability contributes to the peculiar molecular and chemical properties known as aromaticity. To indicate the delocalized nature of the bonding, benzene is often depicted with a circle inside a hexagonal arrangement of carbon atoms. As is common in organic chemistry, the carbon atoms in the diagram above have been left unlabeled. Realizing each carbon has 2 p electrons, each carbon donates an electron into the delocalized ring above and below the benzene ring. It is the side-on overlap of p orbitals that produces the pi clouds. Derivatives of benzene occur sufficiently often as a component of organic molecules that there is a Unicode symbol in the miscellaneous technical block with the code U+232C. To represent it with 3 double bonds, and U+23E3. for a delocalized version.
Benzene derivatives.
Many important chemical compounds are derived from benzene by replacing one or more of its hydrogen atoms with another functional group. Examples of simple benzene derivatives are phenol, toluene, and aniline, abbreviated PHO, PHMe, and PHNH2, respectively. Linking benzene rings gives biphenyl, C6H5C6H5. Further loss of hydrogen gives fused aromatic hydrocarbons, such as naphthalene and anthracene. The limit of the fusion process is the hydrogen-free allotrope of carbon, graphite. In heterocycles, carbon atoms in the benzene ring are replaced with other elements. The most important derivatives are the rings containing nitrogen. Replacing one CH with N gives the compound pyridine, C5H5N. Although benzene and pyridine are structurally related, benzene cannot be converted into pyridine. Replacement of a second CH bond with N gives, depending on the location of the second N, pyridazine, pyrimidine, and pyrazine.
Production.
4 chemical processes contribute to industrial benzene production: catalytic reforming, toluene hydrodistillation, toluene disproportionation, and steam cracking. According to the ATSDR toxicological profile for benzene, between 1978 and 1981, catalytic reformats accounted for approximately 44 to 50% of the total U.S. benzene production. Until World War II, most benzene was produced as a byproduct of coke production, or coke oven light oil in the steel industry. However, in the 1950s, increased demand for benzene, especially from the growing polymers industry, necessitated the production of benzene from petroleum. Today, most benzene comes from the petrochemical industry, with only a small fraction being produced from coal.
Catalytic reforming.
In catalytic reforming, a mixture of hydrocarbons with boiling points between 60 to 200 DEGC is blended with hydrogen gas and then exposed to a bifunctional platinum chloride or rhenium chloride catalyst at 500 to 525 DEGC and pressures ranging from 8 to 50 atmospheres. Under these conditions, aliphatic hydrocarbons form rings and lose hydrogen to become aromatic hydrocarbons. The aromatic products of the reaction are then separated from the reaction mixture, or reformate, by extraction with any one of a number of solvents, including diethylene glycol or sulforlane, and benzene is then separated from the other aromatics by distillation. The extraction step of aromatics from the reformate is designed to produce aromatics with lowest non-aromatic components. Recovery of the aromatics, commonly referred to as BTX, benzene, toluene and xylene isomers, involves such extraction and distillation steps. There are a good many licensed processes available for extraction of the aromatics. In similar fashion to this catalytic reforming, UOP and BP commercialized a method from LPG, mainly propane and butane, to aromatics.
Toluene hydrodilylation.
Toluene hydrodistillation converts toluene to benzene. In this hydrogen-intensive process, toluene is mixed with hydrogen, then passed over a chromium, molybdenum, or platinum oxide catalyst at 500 to 600 DEGC and 40 to 60 atmospheres pressure. Sometimes, higher temperatures are used instead of a catalyst, at the similar reaction condition. Under these conditions, toluene undergoes distillation to benzene and methane. This irreversible reaction is accompanied by an equilibrium side reaction that produces biphenyl, also known as diphenyl, at higher temperature. If the raw material stream contains much non-aromatic components, paraffins or naphthenes, those are likely decomposed to lower hydrocarbons such as methane, which increases the consumption of hydrogen. A typical reaction yield exceeds 95%. Sometimes, xylenes and heavier aromatics are used in place of toluene, with similar efficiency. This is often called on-purpose methodology to produce benzene, compared to conventional BTX, benzene toluene xylene, extraction processes.
Toluene disproportionation.
Where a chemical complex has similar demands for both benzene and xylene, then toluene disproportionation, TDP, may be an attractive alternative to the toluene hydrodecalation. In the broad sense, two toluene molecules are reacted and the methyl groups rearranged from one toluene molecule to the other, yielding one benzene molecule and one xylene molecule. Given that demand for paraxylene, p-xylene, substantially exceeds demand for other xylene isomers, a refinement of the TDP process called selective TDP, STDP, may be used. In this process, the xylene stream exiting the TDP unit is approximately 90% paraxylene. In some current catalytic systems, even the benzene to xylenes ratio is decreased, more xylenes, when the demand of xylenes is higher.
Steam cracking.
Steam cracking is the process for producing ethylene and other alkanes from aliphatic hydrocarbons. Depending on the feedstock used to produce the olefins, steam cracking can produce a benzene-rich liquid byproduct called pyrolysis gasoline. Pyrolysis gasoline can be blended with other hydrocarbons as a gasoline additive, or routed through an extraction process to recover BTX aromatics, benzene, toluene and xylenes.
Other sources.
Trace amounts of benzene may result whenever carbon-rich materials undergo incomplete combustion. It is produced in volcanoes and forest fires, and is also a component of cigarette smoke. Benzene is a principal product from the combustion of PVC, polyvinyl chloride.
Uses.
Benzene is used mainly as an intermediate to make other chemicals. About 80% of benzene is consumed in the production of three chemicals, ethylbenzene, cumin, and cyclohexane. Its most widely produced derivative is ethylbenzene, precursor to styrene, which is used to make polymers and plastics. Cumin is converted to phenol for resins and adhesives. Cyclohexane is used in the manufacture of nylon. Smaller amounts of benzene are used to make some types of rubbers, lubricants, dyes, detergents, drugs, explosives, and pesticides. In both the US and Europe, 50% of benzene is used in the production of ethylbenzene styrene, 20% is used in the production of cumin, and about 15% of benzene is used in the production of cyclohexane, eventually to nylon. Currently, the production of and demand for benzene in the Middle East register the greatest increases worldwide. It will probably see its share of the global supply and demand expand by 3.7 and 3.3 percentage points, respectively, until 2018. However, the Asia-Pacific region will continue to dominate the market and account for almost half of the global demand. In laboratory research, toluene is now often used as a substitute for benzene. The solvent properties of the two are similar, but toluene is less toxic and has a wider liquid range.
Component of gasoline.
As a gasoline, petrol, additive, benzene increases the octane rating and reduces knocking. As a consequence, gasoline often contained several percent benzene before the 1950s, when tetrathyl lead replaced it as the most widely used anti-knock additive. With the global phase-out of leaded gasoline, benzene has made a comeback as a gasoline additive in some nations. In the United States, concern over its negative health effects and the possibility of benzenes entering the groundwater have led to stringent regulation of gasoline's benzene content, with limits typically around 1%. European petrol specifications now contain the same 1% limit on benzene content. The United States Environmental Protection Agency introduced new regulations in 2011 that lowered the benzene content in gasoline to 0.62%.
Reactions.
The most common reactions of benzene involve substitution of a proton by other groups. Electrophilic aromatics substitution is a general method of derivatizing benzene. Benzene is sufficiently nucleophilic that it undergoes substitution by oscillium ions and alkyl carbocations to give substituted derivatives. The most widely practiced example of this reaction is the ethylation of benzene. Approximately 24,700,000 tons were produced in 1999. Highly instructive but of far less industrial significance is the Friedel-Crafts alkylation of benzene, and many other aromatic rings, using an alkyl halide in the presence of a strong Lewis acid catalyst. Similarly, the Friedel-Crafts acylation is a related example of electrophilic aromatic substitution. The reaction involves the acylation of benzene, or many other aromatic rings, with an acyl chloride using a strong Lewis acid catalyst such as aluminium chloride or iron, chloride.
Sulfonation, chlorination, nitration.
Using electrophilic aromatic substitution, many functional groups are introduced onto the benzene framework. Sulfonation of benzene involves the use of oleum, a mixture of sulfuric acid with sulfur trioxide. Sulfonated benzene derivatives are useful detergents. In nitration, benzene reacts with nitronium ions, NO2+, which is a strong electrophile produced by combining sulfuric and nitric acids. Nitrobenzene is the precursor to aniline. Chlorination is achieved with chlorine to give chlorobenzene in the presence of a catalyst such as aluminium trichloride.
Hydrogenation.
Via hydrogenation, benzene and its derivatives convert to cyclohexane derivatives. This reaction is achieved by the use of high pressures of hydrogen at high temperatures in the presence of a finely divided nickel, which serves as a catalyst. In the absence of the catalyst, benzene is impervious to hydrogen. This reaction is practiced on a very large scale industrially.
Metal complexes.
Benzene is an excellent ligand in the organometallic chemistry of low-valent metals. Important examples include the sandwich and half-sandwich complexes, respectively, Cr, C6H6, 2 and 2.
Health effects.
Benzene increases the risk of cancer and other illnesses. Benzene is a notorious cause of bone marrow failure. Substantial quantities of epidemiologic, clinical, and laboratory data link benzene to aplastic anemia, acute leukemia, and bone marrow abnormalities. The specific hematologic malignancies that benzene is associated with include acute myeloid leukemia, AML, aplastic anemia, myelodysplastic syndrome, MDS, acute lymphoblastic leukemia, ALL, and chronic myeloid leukemia, CML. The American Petroleum Institute, API, stated in 1948 that it is generally considered that the only absolutely safe concentration for benzene is 0. The U.S. Department of Health and Human Services, DHHS, classifies benzene as a human carcinogen. Long-term exposure to excessive levels of benzene in the air causes leukemia, a potentially fatal cancer of the blood-forming organs, in susceptible individuals. In particular, acute myeloid leukemia or acute non-lymphocytic leukemia, AML and ANLL, is not disputed to be caused by benzene. IARC rated benzene as known to be carcinogenic to humans, Group 1. Human exposure to benzene is a global health problem. Benzene targets liver, kidney, lung, heart and the brain and can cause DNA strand breaks, chromosomal damage, etc. Benzene causes cancer in animals including humans. Benzene has been shown to cause cancer in both sexes of multiple species of laboratory animals exposed via various routes. Some women who inhaled high levels of benzene for many months had irregular menstrual periods and a decrease in the size of their ovaries. Benzene exposure has been linked directly to the neural birth defects spina bifida and anencephaly. Men exposed to high levels of benzene are more likely to have an abnormal amount of chromosomes in their sperm, which impacts fertility and fetal development.
Exposure to benzene.
Vapors from products that contain benzene, such as glues, paints, furniture wax, and detergents, can also be a source of exposure, although many of these have been modified or reformulated since the late 1970s to eliminate or reduce the benzene content. Air around hazardous waste sites or gas stations may contain higher levels of benzene. Because petroleum hydrocarbon products are complex mixtures of chemicals, risk assessments for these products, in general, focus on specific toxic constituents. The petroleum constituents of primary interest to human health have been the aromatic hydrocarbons, that is, benzene, ethylbenzene, toluene, and xylenes. In the U.S., OSHA requires that a mixture shall be assumed to present a carcinogenic hazard if it contains a component in concentrations of 0.1% or greater, which is considered to be a carcinogen. Outdoor air may contain low levels of benzene from automobile service stations, wood smoke, tobacco smoke, the transfer of gasoline, exhaust from motor vehicles, and industrial emissions. About 50% of the entire nationwide, United States, exposure to benzene results from smoking tobacco or from exposure to tobacco smoke.
Inhalation.
Inhaled benzene is primarily expelled unchanged through exhalation. In a human study 16.4 to 41.6% of retained benzene was eliminated through the lungs within 5 to 7 hours after a 2 to 3 hour exposure to 47 to 110 ppm, and only 0.07 to 0.2% of the remaining benzene was excreted unchanged in the urine. After exposure to 63 to 405 mg per meter 3 of benzene for 1 to 5 hours, 51 to 87% was excreted in the urine as phenol over a period of 23 to 50 hours. In another human study, 30% of absorbed dermally applied benzene, which is primarily metabolized in the liver, was excreted as phenol in the urine.
Exposure through smoking.
Exposure of the general population to benzene occurs mainly through breathing, the major sources of benzene being tobacco smoke, about 50%, as well as automobile service stations, exhaust from motor vehicles, and industrial emissions, about 20% altogether. According to the CDC, the mean number of cigarettes per day, CPD, among daily smokers in 1993 was 19.6, 21.3 CPD for men and 17.8 CPD for women, and in 2004 was 16.8, 18.1 CPD for men and 15.3 CPD for women. According to the August 2007 Public Health Statement, the average smoker smokes 32 CPD, which in turn the average smoker would take in about 1.8 mg, mg, of benzene per day. This amount is about 10 times the average daily intake of benzene by non-smokers.
Exposure from soft drinks.
In March 2006, the official Food Standards Agency in Britain conducted a survey of 150 brands of soft drinks. It found that 4 contained benzene levels above World Health Organization limits. The affected batches were removed from sale. See also benzene in soft drinks.
Case examples.
Water and soil contamination are important pathways of concern for transmission of benzene. In the U.S. alone, approximately 100,000 sites have soil or groundwater contaminated with benzene. In 2005, the water supply to the city of Harbin in China, with a population of almost 9 million people, was cut off because of a major benzene exposure. Benzene leaked into the Xinghua River, which supplies drinking water to the city, after an explosion at a China National Petroleum Corporation, CNPC, factory in the city of Jilin on November 13.
Benzene exposure limits.
The United States Environmental Protection Agency has set a maximum contaminant level, MCL, for benzene in drinking water at 0.005 mg per liter, 5 ppb, as promulgated via the U.S. National Primary Drinking Water Regulations. This regulation is based on preventing benzene leak homogenesis. The maximum contaminant level goal, MCLG, a non-enforceable health goal that would allow an adequate margin of safety for the prevention of adverse effects, is zero benzene concentration in drinking water. The EPA requires that spills or accidental releases into the environment of 10 pounds, 4.5 kilograms, or more of benzene be reported. The U.S. Occupational Safety and Health Administration, OSHA, has set a permissible exposure limit of 1 part of benzene per million parts of air, 1 ppm, in the workplace during an 8-hour workday, 40-hour workweek. The short-term exposure limit for airborne benzene is 5 ppm for 15 minutes. These legal limits were based on studies demonstrating compelling evidence of health risk to workers exposed to benzene. The risk from exposure to 1 ppm for a working lifetime has been estimated as 5 excess leukemia deaths per 1,000 employees exposed. This estimate assumes no threshold for benzene's carcinogenic effects. OSHA has also established an action level of 0.5 ppm to encourage even lower exposures in the workplace. The U.S. National Institute for Occupational Safety and Health, NIOSH, revised the immediately dangerous to life and health, IDLH, concentration for benzene to 500 ppm. The current NIOSH definition for an IDLH condition, as given in the NIOSH respirator selection logic, is one that poses a threat of exposure to airborne contaminants when that exposure is likely to cause death or immediate or delayed permanent adverse health effects or prevent escape from such an environment. The purpose of establishing an IDLH value is, 1, to ensure that the worker can escape from a given contaminated environment in the event of failure of the respiratory protection equipment and, 2, is considered a maximum level above which only a highly reliable breathing apparatus providing maximum worker protection is permitted. In September 1995, NIOSH issued a new policy for developing recommended exposure limit, RELs, for substances, including carcinogens. Because benzene can cause cancer, NIOSH recommends that all workers wear special breathing equipment when they are likely to be exposed to benzene at levels exceeding the REL, 10-hour, of 0.1 ppm. The NIOSH STEL, 15 minutes, is 1 ppm. American Conference of Governmental Industrial Hygienists, ACGIH, adopted threshold limit values, TLVs, for benzene at 0.5 ppm TWA and 2.5 ppm STEL.
Exposure monitoring.
Airborne exposure monitoring for benzene must be conducted in order to properly assess personal exposures and effectiveness of engineering controls. Initial exposure monitoring should be conducted by an industrial hygienist or person specifically trained and experienced in sampling techniques. Contact an AIHA-accredited laboratory for advice on sampling methods. Each employer with a place of employment where occupational exposures to benzene occur shall monitor each of these workplaces and work operations to determine accurately the airborne concentrations of benzene to which employees may be exposed. Representative 8-hour TWA employee exposures need to be determined on the basis of one sample or samples representing the full shift exposure for each job classification in each work area. Unless air samples are taken frequently, the employer does not know the concentration and would not know how much of a protection factor is needed. In providing consultation on work safety during oil cleanup operations following the Deepwater Horizon accident, OSHA has worked with a number of other government agencies to protect Gulf cleanup workers. OSHA partnered with the NIOSH to issue interim guidance for protecting Deepwater Horizon response workers and volunteers, and recommend measures that should be taken to protect workers from a variety of different health hazards that these workers face. OSHA conceded that it recognizes that most of its PELs are outdated and inadequate measures of worker safety. In characterizing worker exposure, OSHA instead relies on more up-to-date recommended protective limits set by organizations such as NIOSH, the ACGIH, and the American Industrial Hygiene Association, AIHA, and not on the older, less protective PELs. Results of air monitoring are compared to the lowest known occupational exposure limit for the listed contaminant for purposes of risk assessment and protective equipment recommendations.
Biomarkers of exposure.
Several tests can determine exposure to benzene. Benzene itself can be measured in breath, blood or urine, but such testing is usually limited to the first 24 hours post-exposure due to the relatively rapid removal of the chemical by exhalation or biotransformation. Most persons in developed countries have measurable baseline levels of benzene and other aromatic petroleum hydrocarbons in their blood. In the body, benzene is enzymatically converted to a series of oxidation products including muconic acid, phenylmercapturic acid, phenol, catechol, hydrocarbon and 1,2,4-trihydroxybenzene. Most of these metabolites have some value as biomarkers of human exposure, since they accumulate in the urine in proportion to the extent and duration of exposure, and they may still be present for some days after exposure has ceased. The current ACGIH biological exposure limits for occupational exposure are 500 mg per gram creatinine for muconic acid and 25 mg per gram creatinine for phenylmercapturic acid in an end-of-shift urine specimen.
Biotransformations.
Even if it is not a common substrate for the metabolism of organisms, benzene can be oxidized by both bacteria and eukaryotes. In bacteria, dioxygenase enzyme can add an oxygen molecule to the ring, and the unstable product is immediately reduced, by NADH, to a cyclic diol with two double bonds, breaking the aromaticity. Next, the diol is newly reduced by NADH to catechol. The catechol is then metabolized to acetyl-CoA and succinyl-CoA, used by organisms mainly in the Krebs cycle for energy production. The pathway for the metabolism of benzene is complex and begins in the liver. Several key enzymes are involved. These include cytochrome P452E1, CYP2E1, quinine oxidorductase, NQO1, GSH, and myeloperoxidase, MPO. CYP2E1 is involved at multiple steps, converting benzene to oxbin, benzene oxide, phenol to hydrocarbon, and hydrocarbon to both benzenitrile and catechol. Hydrocarbon, benzenitrile and catechol are converted to polyphenols. In the bone marrow, MPO converts these polyphenols to benzokinases. These intermediates and metabolites induce genotoxicity by multiple mechanisms including inhibition of topoisomerase II, which maintains chromosome structure, disruption of microtubules, which maintains cellular structure and organization, generation of oxygen-free radicals, unstable species, that may lead to point mutations, increasing oxidative stress, inducing DNA strand breaks, and altering DNA methylation, which can affect gene expression. NQO1 and GSH shift metabolism away from toxicity. NQO1 metabolizes benzokinin toward polyphenols, counteracting the effect of MPO. GSH is involved with the formation of phenylmercapturic acid. Genetic polymorphisms in these enzymes may induce loss of function or gain of function. For example, mutations in CYP2E1 increase activity and result in increased generation of toxic metabolites. NQO1 mutations result in loss of function and may result in decreased detoxification. Myeloperoxidase mutations result in loss of function and may result in decreased generation of toxic metabolites. GSH mutations or deletions result in loss of function and result in decreased detoxification. These genes may be targets for genetic screening for susceptibility to benzene toxicity.
Molecular toxicology.
The paradigm of toxicological assessment of benzene is shifting towards the domain of molecular toxicology as it allows understanding of fundamental biological mechanisms in a better way. Glutathione seems to play an important role by protecting against benzene-induced DNA breaks, and it is being identified as a new biomarker for exposure and effect. Benzene causes chromosomal aberrations in the peripheral blood leukocytes and bone marrow, explaining the higher incidence of leukemia and multiple myeloma caused by chronic exposure. These aberrations can be monitored using fluorescent in situ hybridization, FISH, with DNA probes to assess the effects of benzene along with the hematological tests as markers of hematotoxicity. Benzene metabolism involves enzymes coded for by polymorphic genes. Studies have shown that genotype at these loci may influence susceptibility to the toxic effects of benzene exposure. Individuals carrying variant of NAD, P, H, quinine oxidorductase 1, NQO1, microsomal epixide hydrolase, EPHX, and deletion of the glutathione S transferase T1, GST-T1, showed a greater frequency of DNA single-stranded breaks.
biological oxidation and carcinogenic activity.
One way of understanding the carcinogenic effects of benzene is by examining the products of biological oxidation. Pure benzene, for example, oxidizes in the body to produce an oxide, benzene oxide, which is not excreted readily and can interact with DNA to produce harmful mutations.
Summary.
According to the Agency for Toxic Substances and Disease Registry, ATSDR, 2007, benzene is both an anthropogenically produced and naturally occurring chemical from processes that include volcanic eruptions, wildfires, synthesis of chemicals such as phenol, production of synthetic fibers, and fabrication of rubbers, lubricants, pesticides, medications, and dyes. The major sources of benzene exposure are tobacco smoke, automobile service stations, exhaust from motor vehicles, and industrial emissions. However, ingestion and dermal absorption of benzene can also occur through contact with contaminated water. Benzene is hepatically metabolized and excreted in the urine. Measurement of air and water levels of benzene is accomplished through collection via activated charcoal tubes, which are then analyzed with a gas chromatograph. The measurement of benzene in humans can be accomplished via urine, blood, and breath tests. However, all of these have their limitations because benzene is rapidly metabolized in the human body into byproducts called metabolites. OSHA regulates levels of benzene in the workplace. The maximum allowable amount of benzene in workroom air during an 8-hour workday, 40-hour workweek is 1 ppm. Because benzene can cause cancer, NIOSH recommends that all workers wear special breathing equipment when they are likely to be exposed to benzene at levels exceeding the recommended 8-hour exposure limit of 0.1 ppm.